Welcome, everybody. Thank you for being here. Get yourselves ready with a notebook. Grab yourself a pencil or a pen. Whichever you choose to write with is fine. This is math from the void. Math coming at you pretty much out of nowhere. And today we have a problem from the 1993, I know, it's pretty old, Calculus AB exam. This is a differential equation type problem. So if you're in AB and you haven't learned about differential equations thoroughly and you're not comfortable with them, make sure you're practicing every day. All right, I'm going to give you about 12 minutes to solve this one. It is a little bit shorter. And then when you're ready, you can join back, see how we do it here. And here we go. P of t represents the number of wolves in a population at time t, where t is greater than or equal to 0. The population is increasing at a rate. So we're going to call that dp dt. And the rate is directly proportional, which means that we have some multiplier, usually called k, is directly proportional to something. What is it directly proportional to? 800 minus p of t, which is the current amount of population. And a lot of biological models, population models work like this, where the change in population depends on the current population. Right? If you only have 5 animals making babies, that's going to be a different increase in babies per year than if you have 12,000 animals making babies each year. So it makes sense that the rate of the population is directly proportional. And notice that this is always a positive. It says that the population is increasing. So in this case, we know that k is likely greater than 0, right? Because it's unlikely that the population is over 800, otherwise this would be a negative. But it's not impossible. Actually, looking at these values here, I see that it's never really past 800, so it makes sense. Seems to make sense. And it also seems to be going up. See that? P0 is 500, so we start with 500 wolves, and then 2 years later we have 700 wolves. How beautiful. We've added 200 wolves to the pack. Okay, let's get ready with part A. Part A says, if this initial condition is true, find P of t in terms of t and k. So we're not going to have k solved yet. That's really important. And I also want to mention something that is definitely worth mentioning here. Oops. When do we have a derivative that's proportional to the original function in any way? This is some kind of exponential logarithmic model. I mean, it's exponential, but you should be thinking that it's somehow proportional. Well, yeah, I should remove the fact that I put logarithm there. It's some kind of exponential growth model. And something worth remembering now that we've pointed that out is that exponential growth models can only be completely solved if we have 2 initial conditions. And here we're given 1 initial condition. So it does also make sense that we're not going to be able to solve for k. We are going to be able to solve for the plus c, but it's going to be in terms of k. All right, so let's get started with this. We have dp dt. Oops. Equals k times 800 minus p. I'm not going to put p of t. I'm just going to put p for laziness. And we need to get all the variables separated. So we need the dt stuff on one side. I'm going to multiply that on the right. And we need all the p stuff on the left. So I'm going to divide 1 over 800 minus p dp. And now we're ready to integrate both sides. This is going to give us negative ln of 800, well, I should say absolute value, just because there are some negatives involved, minus p equals kt plus c All right, and we want to solve for p of t. That's what we're finding. So we have to work this down until we get p. Let's go ahead and use the rule for logarithms of putting the negative on there. So this is ln of absolute value 1 over 800 minus p equals kt plus c. And we can use the initial condition now if we really wanted to. But let's put things in terms of e. So if we raise e to the power, this is going to be 1 over 800 minus p. And on this other side, we're going to have e to the power kt plus c. All right, we're almost done. So this is looking actually kind of like a logistic growth model. I guess that was why I put logarithmic and some kind of like logistic, not logarithmic, but logistic growth model. Okay, so what can we do here? Let's go ahead and plug in the initial condition now. Let's use the fact that t equals 0 and p equals 500. So now we're going to have 1 over 300 equals, well, since t is 0, this is just e to the c. But we're just going to call this its own constant c. And here's why. It's because we're going to express this portion a little bit better. We're going to express this as e to the kt times e to the c. And then we can just call this its own new constant, c e to the kt. Got it? So that's what we have now. We have 1 over 300 e to the kt equals 1 over 800 minus p. All right, and there's a few different ways that we can deal with this. The way that I prefer is to just flip this, completely flip it. So this is going to be 300 over e to the kt equals 800 minus p. So we can add p and subtract the 300 over e to the kt, and we have p equals 800 minus 300 over e to the kt. And if you'd really like to get all of that, how should I say, in one denominator, like in one fraction, you can. It's not very difficult to do it. It'll say 800 e to the kt minus 300, and then this is all over e to the kt. If that's easier for you, by all means, go ahead and make it happen. And you'll notice that as we plug in 0, this model still works. If I plug in 0, this turns into a 1, so 800 minus 300, and this also turns into a 1, 500. That was satisfying our initial condition. So this is perfectly valid. There are other ways to write this equation. Like, you don't have to write it like this, but just how I chose to write it. Okay, now for part B, let's solve for k using this other initial condition. Find k, that's the goal. So t is 2, p is 700. We just got to plug and chug now that we have a model. Plug and chug that. So we're going to have 700 is equal to, and obviously k is going to be some kind of gnarly term. It's not going to be an easy term to determine. We'll use a calculator or something. E to the 2k minus 300 over e to the 2k. And here's where things work out really nicely. We're just going to multiply both sides. That's why I choose this model. We're going to multiply both sides by e to the 2k. Even though it took a little bit of work to get it into this format, it's so worth it. That's pretty straightforward. So we add 300 on the other side, subtract 700 on this side, and we get 300 equals 100. Oh, whoops, lost my e. E to the 2k. And so we just get 3 equals e to the 2k. Therefore, 2k equals ln of 3, and k is simply going to be ln of 3 over 2. So I guess it wasn't that gnarly. We could just leave it like that. We don't necessarily have to get, if this is a calculator problem, sure, go ahead and get a value, but we don't necessarily have to get a value on that. Okay, now for part C, this one is really interesting. Find the limit, and if you got a different expression as t goes to infinity, if you got a different expression for p of t, this might be easier or it might seem more difficult. If you used this expression for p of t, which is fine, this limit does seem pretty dang easy. Because we know that as t gets really big, this just goes to 0, so obviously that limit is 800. But we should have suspected that it's somewhere around 800, or at least that something funky happens at 800, because the derivative, notice that this equals 0 if p equals 800, which means what? That means that the population's slope, or the change in the population, is 0 at that point. It's steady at that point, sort of called a stable point. And so it seems to reason that if it stops growing, then the population's stable there at 800, right? So let's just keep that in mind. That should have been sort of in the back of our mind at the beginning of analyzing the problem, but let's calculate the formal limit. Well, maybe not the formal limit. The formal limit is pretty intense. You'll learn that kind of stuff in university calculus. In any event, limit as t goes to infinity of what I have here, which is 800 e to the kt minus 300 over e to the kt. Basically, these get really large, while this just stays pretty insignificant. And that's going to leave us with 800 over 1. So this is really just going to go to 1. Like I said, if you expressed it as this p of t, it might have been quicker to see it, but that's okay. The same principle applies, is that the 300 divided by this gets really small, it becomes insignificant, whereas this term is 800 times as much as the bottom, so it's not insignificant, it stays steady at 800. So, oops, why did I write 1? It's going to be 800 wolves, that's right around that limit. Okay, like I promised, this was a pretty quick problem. Some reminders are that when you have 2 bits of information, 2 initial conditions for a differential equation in AP/AB calculus, more often than not, it's going to be some kind of an exponential model. In this case, it was a logistic, which is a type of exponential model. It's just got a little bit of slightly different features, like a maximum, like a capacity. So the wolves kind of grow like that, and they reach some sort of boundary. You guys might have seen that curve once or twice in pre-calculus. I don't know how often they bring it up in calculus, but this could come up on the AP exam, so I want you to be familiar with it. This is sort of what the graph looks like, and you can see that it's always increasing. So when we only have small amount of wolves, it's not going to be increasing very quickly, but then at some point we're increasing a lot. There's a lot of wolves making babies. And then it starts to taper off because, of course, resources are limited. There's no shortage of reproduction, but there is a limitation to how many resources they have as a society, maybe how much space they have physically, land. So things like that are factors which sort of contain or limit the capacity of a population. Anyway, I can go on and on about differential equations and how they explain pretty much everything in the world, but I think that's enough blab out of me. I'll see you guys next time in the void.